What's going on, everybody? It's Mr. Gus, and I'm back in the physics classroom. Today, we are looking at a new kind of circle. We've got a horizontal circle, like a record player. In fact, it is a record player. And today, we're going to look at the forces that hold objects in a horizontal circle, particularly our record player. And we're going to look at how friction, that force, can be, how we can determine its maximum capability, its maximum ability to hold things in a circle. We have to know about centripetal force. Centripetal force is kind of a requirement force. It kind of tells us how much force is required to hold an object in circular motion. If that force can be, that requirement for the force can be met by either gravity or tension or friction, then objects will maintain their circular path. If for some reason those forces, gravity, friction, tension, are not strong enough to hold objects in their circular path, things will go flying off tangentially out of their circle. Strings will break, cars will slide, cars will leave the road over hills, things like this. So today, we're going to look at the maximum amount of friction that will hold something in a circular path. So in order to do that, come on, let's go check our setup. Let's go back here. So what I have back here is this neat little record player, which you can see right here. And on the record player, if the camera will focus, you might be able to see there are some measurements. I've got this plate here, and this plate has measurements that measure all the different radii. So it goes from 0 centimeters, obviously at the middle, 1, 2, 3, 4, all the way out to 12 centimeters, and then the edge of this thing is 13 centimeters. So I've got kind of a record here that has measurements on it that I can now take the radius of. And so when I turn the record player on, I hope you can see it starts to spin. I try to keep it as level as possible, so we're really only looking at friction here. And so what I can do is take an itty-bitty little mass here and place it on my record player, and you can see right now that the force of friction is strong enough, it meets the requirements of the centripetal force to hold this mass in place. But as I move this mass, if I don't knock it over, as I move this mass outward, what we'll see is that at some point it moves too fast. At some point the record player's radius is too large, and the centripetal force required to hold my mass in place is not being met by friction. Friction is not strong enough. The connection, the coefficient of friction is not high enough to hold my mass in the circle, so it goes sliding off. So there's a certain point, if I keep bumping this thing out, at which friction is no longer able to pull this thing in a circle. And so that's our task today. At the front board, our main question was, what is the coefficient of maximum static friction? What is the maximum static friction that is present there? And let's use that to find my coefficient of static friction. So let's talk through some things. Before we take our data, let's go figure out what data is necessary for us to take. So every time we approach a problem, our first step is to draw a picture, then write an equation, and then consider our problem. So here we go. I've got my mass sitting here on a record player, moving in a horizontal circle. I know that there's a weight force, which is Fg. I know that there is a support force, or Fn, and this object is not accelerating vertically, so those forces must be balanced. I also know that the force holding it in the circle is not just the force of friction, but it is the force of friction static. It is holding this thing from moving. Even though it is rotating, it is not sliding, and so it is static friction. From here, let's write my Fnet equations. I've got Fnet in the y direction. That's going to be Fg minus Fn. That equals 0 newtons. It's not moving. What I find from there is that Fg is equal to Fn, or is equal to mg. Folks, that's a pretty common, pretty routine substitution that we make, so let's remember that one is there. The other direction that I'm seeing forces is not necessarily in the x direction alone. It would be in the centripetal direction, radially inward, because it's changing directions. It's constantly pointed inward. So I'll see that the force of friction static is equal to F net C. Force of friction is mu times Fn, and any centripetal force is mv squared over r. I'm ending up with this equation here. Mu Fn equals mv squared over r. I can continue to expand this because I know that Fn equals mg. So let's go mu mg equals mv squared over r. Well, masses will drop out. If my goal is to find the coefficient of friction, then my equation had better be in terms of coefficient of friction. So let's find out what is coefficient of friction dependent upon. Coefficient of friction is v squared over r times baby g. Let's think about what these things might be. All right, baby g, that's a constant. I don't need to measure that. R, that's a radius. I've got a way to measure radius on the turntable on the record player, so I can measure R. Now measuring velocity, like sidebar, remember velocity in a circle is circumference over period. So in order for us to think about that, I'd have to do 2 pi r, there's that radius again, and I'd have to know the period. All right, so I can measure period and I can measure radius, and both of those things wrapped up together will give me mu. Okay, I can do those things. So now I've got a plan. So if I think about a plan or things to measure, I should be measuring radius and period. These are the 2 things that I need to measure. Now, the question is, what radius? Because I was back there playing around with a turntable, moving that mass in and outward. So what radius am I concerned with? Well, again, I am looking for what is the mu s for mass and the record player. Well, the coefficient of static friction is only related to the maximum static friction. It's only related to like how much force can 2 surfaces apply on each other in a maximum way. Static friction is one of those weird frictions that like increases the more and more you push on it until you overcome its maximum, its threshold. So we're looking for the maximum friction. So when I think about this radius, this is the radius at which static friction is applying its maximum force. Its absolute maximum. It's doing the best it can. So I'm going to look for the radius right before my mass goes flying off. All right? So that's what we're looking for. We're looking for the radius at which that mass is just about to slide and turn from static friction into kinetic friction. So that's what we're looking for. Let's go back and look. Now, as we travel back here, let's talk about what a record player does. And maybe your parents know this, or maybe you're super into records. It's coming back. But on a record player, there are 3 different speeds this record player can move. It's usually based on the size of the record player, but there's 33 RPMs, 45 RPMs, and 78 RPMs. This is how fast the record player moves. It's a frequency. It's revolutions per minute. So I don't actually need to measure period. I just need to know what my setting is, and based on my setting, I can then calculate from frequency over into period. So let's think about that. I'm going to go ahead and set this thing to 45 RPMs. So we know I don't need to measure period. It's just 45 RPMs. You can write that down, and we can come up with the period later from that frequency. Most importantly, let's turn this thing on. So now it's moving, and we can start gathering some data. So you can see that it's moving. Here's my mass. If I put it at a small radius, it's moving. So this radius isn't large enough. So I'm going to start from the middle and work my way out, and we'll start seeing whether or not friction is capable of holding this thing in a circle. So right now I'm at about 3.5 centimeters, and so 3.5 centimeters is not a large enough radius. Let's jump out to 5 centimeters. If I jump out to 5 centimeters, it is still held in its spot. Let's jump out to 6 centimeters. If I jump out to 6 centimeters and let it go, it stays put at 6 centimeters. Let's go out a little further. Let's say 7 centimeters. If I jump out there at 7 centimeters, ooh, it starts to move at 7 centimeters. Let's try that again. 7 centimeters. I'm going to try to do my best. Ooh, okay, it is right around 7 centimeters. This thing moves, but it doesn't move very much. I'm going to go 6.5. Right at 6.5, let's see. Well, it did slide a little bit, but it slid out to 7 centimeters, and it's still being held there. So it's possible that, when I start it from rest, the jerking motion or that acceleration motion causes it to move. Right now, it's at 7 centimeters and is held put. Let's see if I can try at 7 centimeters slowly. Yeah, no, it means 7 centimeters. Let's see if I go slower at 7 centimeters and then pick up my speed. Oh, yeah, it holds at 7 centimeters. That's weird. Does it hold at 8 or 7.5? Okay, it's going. If I speed it up a little bit. No, okay. So it's going to hold at 7. 7 centimeters is the radius at which it will still hold, even though we saw it fly off first. It may have been because the surfaces slid because of the inertia of the object. It was wanting to stay at rest and then slid, and then once we broke static friction. So it looks like my radius is 7 centimeters, or 0.07 meters. Now my period, I said, was 45 revolutions per minute. That's a frequency, though, because it's revolutions per minute. I want to flip that. I want to know how many minutes per revolution. So it's actually, we would say it would be 60 seconds per 45 revolutions. That is my period. So it's a little equation. We could easily go ahead and solve that equation. So let's do 60 divided by 45. So 1.33 is my period. 1.33 seconds. That's the period. That's the radius. It looks like I've got everything I need now to go ahead and find this coefficient of friction. So at home, go ahead, find your coefficient of friction. Notice it doesn't depend on mass. The mass does not dictate the coefficient of friction. Coefficient of friction is dependent on what the two materials are made of and what you're asking the two surfaces to do. So if we recap, let's recap. This recap we talked about horizontal circles like the record player. We talked about the centripetal force being a requirement force. It tells me how much force is required to keep objects moving in a circle. And in this case, our centripetal force was the force of static friction. And we were checking to see at what point is friction not enough force to keep our mass moving in this horizontal circle. And for us, what we found was that a radius of 0.07 meters is that spot, right past 0.07 meters or 7 centimeters. Right past that point, static friction, is not enough force to maintain circular motion, and therefore we see it slide off in a tangential direction to where it was. Okay? If you have questions, ask me in class, drop them in the comments. Until next time, see ya!